Hey everyone, welcome to virtual physics class. Can everyone hear me?
Yep.
Excellent. How's everybody doing?
Good, good.
Glad to hear it. This is quite weird. I'm not sure I've ever done a live virtual class before, so I probably will have some things to figure out as we go along, but that's okay. I would like all of you to not be shy about asking questions. I think I'll be a little more attentive to the chat this time. If you want to throw a question up there, that's cool. But you should also just feel free to unmute yourself and pipe up, ask a question, make a comment. I'd like this to be as similar to a regular class as we can possibly make it. Uh, looks like people are moving on. Okay, cool. We took a week and a half ago, we took exam 3. I finally finished grading that stuff last night. Let me share with you a histogram. There you go, you can see this. This shows the average of this particular exam. It was a harder exam than the first two, I think, and the average reflected that. First two exams had been in the high 70s, 78 and 77 maybe. This one was a flat 70 average, and probably about right given the difficulty of the test. So I still was a decent average of 35 out of 50, a little bit above 70. And here's the distribution again, pretty flat, which is interesting. But you know, only one score really falling below 50%, and it's pretty amazing. I did crunch the numbers yesterday, the numbers that I have. There's nobody who is even getting a D at this point in the class. Everybody who started the class, all 34 of us, are passing it without even dipping down in the D's. So I know there's some people who aren't scoring as well on some of these exams as you would like, and I understand that, but know that from my perspective, this looks pretty good. And I've never taught this class and not given at least one person a D or an E. So I would be very happy if I didn't have to do that again this semester. So kudos to you. Again, I have all of these exams sitting here, a big stack of them. I'm wondering, obviously, if you want your exam, you can't just come and pick it up anymore. Considering what the best way to do this is, I could just unstaple them all, scan it all in a big file, and then send all of them to you. But if you're not interested in seeing it, then that seems like a waste. So how about if you're interested in having your scanned version of the exam, just send me an email and I'll get it out to you. Okay. Any questions about that? Okay, let's talk about the final. Let me pull up my calendar. I had it getting from somebody today who pointed out that I had said that the final would be on December 17th and pointed out that that was a Thursday. I clearly got that wrong. We will not be having the final on December 17th. My thought now is to have it on Friday the 18th. So we actually could move it back to the 21st if we wanted to, but I don't really want to be grading on the 22nd and 23rd. So I think I can get all the material covered by the 16th, which would be that Wednesday, 2 weeks from this Wednesday. So if we have the exam on Friday the 18th, that gives us, including today's class, 3 this week, 3 next week. That's 6 classes, a 7th class on Monday the 14th. And I think that might even be enough to do it all. We could have maybe a review session, or if I have a little bit more material to cover on Wednesday the 16th, so be it. There would be a Kappa due Thursday the 17th in the evening again. And then my thought now is I would open up the exam at say 8 o'clock in the morning on Friday the 18th. and you would have, I don't know, 12 hours between 8 a.m. and 8 p.m. to finish it, or at least to start it on that Friday. And then I would have the weekend to grade it, and hopefully exams would be ready to be submitted Monday morning. Any questions about how any of that would work? I didn't hear a lot of objection last time to my idea to both discourage cheating and also to make it easier for people who may not be in the best home situation in terms of studying and quiet time to take exams, to both take all 4 exams we've taken this semester, throw out both the lowest and the highest, and go with the middle 2, and calculating your final grade. It seems to disincentivize the kinds of behavior that I want to disincentivize. Hearing no objections to that. If you have strong objections, you can send them my way, but that's how I'm planning to do it right now. It will be an asynchronous exam. It will be an hour long. It will be similar in length and format to the previous exams, except all of you will be taking it in a virtual format. You'll be writing it on separate sheets of paper, and then uploading those pieces of paper to Canvas after an hour. So there's a new homework up. It's been up for a week or so. It's due this Thursday. You have, as of the extra lecture that I posted over break, all the information you need to complete all of it. So you should be able to take a look at that. Let me just share it real quick. This is my version. So just be aware that one of these, number 4, is a difficult problem. So we spent some time the last time we were together, a week ago today, talking about the Planck curve, and we wrote down the actual Planck curve, the Planck let me just prepare you for number 4 a little bit. And let me change my camera. Okay, you seeing this camera now? Okay, so here is the Planck curve that we wrote the equation for this thing, right? And this was intensity as a function of wavelength. And, this was something that had, lambda to the 4th or whatever, and a 1 over e to the something minus 1. Pretty complicated function. Wien's law tells us at a given temperature what wavelength this thing peaks at, right? And so you can take the Planck curve formula and calculate what this value is, right? You have to take the derivative of it and set it equal to 0, and then and it's a transcendental equation, but you can solve it for what that lambda max has to be. You can do the same thing for number 4. You are given what the peak frequency is of the black body radiation, and you're asked you're given the peak frequency, and you're asked to find the peak wavelength, right? So you need to figure out what the temperature is. Once you know the temperature, you can use Wien's laws. Temperature with Wien's law will give you the peak wavelength. But there is no equivalent Wien's law. You didn't see what I wrote there. There is no equivalent Wien's law, at least isn't usually written down, for frequency space. And it's not just a matter of lambda max times frequency peak, right, does not equal C, right? Wavelength times frequency does equal C, but you can't just take this lambda max and multiply and divide it by C, or take this C and divide it by lambda max to get frequency max. That actually doesn't work because, again, they're slightly different functions. IF is not the same as I lambda. And so you actually have to solve this in a numerical way. There's several different ways to do it. The hard way is to take IF, take the derivative, set it equal to 0, and derive your own Wien's law for frequency space. That's a very robust way to do it, but it's difficult. If you want that challenge, you can go ahead and do it if you want to. The simpler way to do it is simply take this IF formula, put it into Excel and use solver to figure out, given this frequency, what temperature this has it so that this frequency is a maximum. And there's a couple of different ways to do that, and I'll let you sort of figure out how to do that. But you can certainly use solver and just think about the finding the temperature numerically using solver at which it has a particular peak at this frequency. And then once you have that temperature, you can use that temperature with Wien's law to get the maximum peak wave. Okay, so that is by far the most difficult problem on this set. It does require some numerical solving, but that's at least the bounds for how to figure it out. Okay, so have fun with that. Great. So hopefully you have watched the video on the photoelectric effect. And we're now ready to get started on our kind of last unit of the entire semester, which is special relativity. So let's get started. You may have noticed I posted an announcement. Actually, I sent you an email and posted an announcement today. So let me cover that first. The announcement, the email was involving a survey. Dr. Fletcher runs a lot of the physics teacher education programs here at Geneseo. I know some of you are interested in that, but he needs as many physics majors as possible to take this survey to help him validate his own results for his teachers. And so it would be very helpful if you could take 15, 20 minutes sometime the next week to open that up. It's just a bunch of opinions about attitudes and thoughts and things about the physics teacher education career in general. So even if you're not planning to be a physics teacher, that's okay. Even more so, we're interested in seeing sort of what a typical physics major thinks about these things. So please do take some time to fill that out. There's another reflective writing up again this week. I think it's an interesting one about letters of recommendation that I get asked to write every year. And you might not know what goes into those kinds of things. And it might be helpful for you to know what goes into some of those kinds of things. So you can check that out also. All right, but without further ado, let's talk about relativity. So I can't remember, I meant to say this during the photoelectric lecture, but I may not have. Albert Einstein won a single Nobel Prize. He probably was deserving of 3 or 4. But the single Nobel Prize that he won was for explaining the photoelectric effect. It was for that 1905 paper that explained why it takes, and how basically explaining that photons are a thing, and using that to explain the photoelectric effect. He did not win one for special relativity. He did not win for general relativity or any of the other things that he did. So that's noteworthy in itself for the photoelectric effect. But 1905 was a pretty amazing year for Einstein. He wrote no fewer than 3 or 4 papers that either created entire new branches of physics or completely redefined old branches of physics. It's sort of his most amazing year of discovery ever. So this whole rest of the semester is going to be stemming from a paper that Einstein wrote in 1905. And so let's put ourselves back in 1905 and think about what the prevailing systems of thought were. Let me go back to this camera. Okay, excellent. So it's 1905. It was assumed up until that point that light must travel through a medium. It must be that there is some medium that light travels through. Why did people assume that? Because every single other wave that was known operated under this scenario. There was some medium through which that wave traveled. Sound waves need the air molecules in the room to be able to travel. Obviously, waves on a string need the string, waves on the water need the water. Any wave that you could think of needed some medium to travel through. Light seemed to be the exception, but it was thought that that couldn't possibly be an exception. Light must need some medium also. Now, the fact that you can go outside at night and see the moon, the fact that we get sunlight, the fact that we're seeing stars at night says that if there is a medium that light is traveling through, it must be pervasive. It must expand and spread through the entire universe. And so, what must this all-pervasive thing be? Well, they didn't really know what it was, but they called it the ether. And so they thought that this stuff must be spreading through the universe to provide light with some medium to travel to us. Otherwise, how could it get to us? How would we be able to see the sun and the moon and the stars? So this is the luminiferous ether, which is really a great name. Luminiferous meaning ether, meaning sort of a, stuff that's spread through the universe. Luminiferous means it's the propagation mechanism for light. So I know you've done some experiments this semester that have talked about this at some level. Specifically, there was one of the most famous experiments of the early 19th century, early 1900s anyway, was the Michelson-Morley experiments. And this was done in 1887, 8 years before Einstein wrote his paper. And if you probably have read about this, Michelson and Morley says, okay, if there is a luminiferous ether and we're traveling through it, it should be that we should be able to measure the difference in the speed of light moving in one direction as opposed to another, right? So for instance, if you're in sound, if you're in air, right, and you're moving through that air, you can actually measure a difference between the speed of sound moving towards you, in the direction of motion and anti the direction of motion, right? You'll see it traveling faster as you move in the direction that you're moving, because the speed of light is sort of constant from a set reference point, meaning the standard of rest of the air. There's probably then some rest frame for that ether, and if we're traveling through that ether, then we should be able to measure a speed of light difference pointing in one direction or the other. And they used a Michelson interferometer, which, as you know, is very good at measuring very small differences and changes in things. And they thought, they knew the speed of the Earth around the sun. They knew the speed of the sun around the galaxy. They had some idea for how fast we were moving in some way through this ether. And they thought they had enough resolution to be able to pick out the differences in the speed in different directions. And they tried it once and they got nothing. And they were like, well, that's weird, but maybe it's safe. Maybe we just happen to be at rest at that particular point. If we wait, the Earth is spinning 6 hours, or at worst 6 months, we will be moving at a different rate relative to the ether. We should be able to measure something. They redid it 6 hours later, nothing. They redid it 6 months later, nothing. They still could not measure any difference in the speed of light, no matter which direction they oriented their interferometer. So this is perhaps the most famous null result of all time. Usually when you're doing an experiment and you don't find the thing you're supposed to be finding, you consider that a bad thing. And they thought it was a bad thing at first too, but it opened the door to lots of other things. So basically, null result, speed of light is constant, constant no matter, let's say, Earth's frame. This is, hopefully you can read all that. Okay. There were lots of smart people who didn't like the idea of the ether going away, who proposed all kinds of interesting ways to save it, including frame dragging, which is like, okay, maybe we're pulling the luminiferous ether with us, and that inside our experimental room, we're not moving through the ether, the ether's moving with us. But eventually experiments were done that proved that was not the case either. And so eventually you had to eliminate the idea of an ether altogether. It just didn't work. And so this leads to Einstein making that as assumption. Okay, what if there is no ether? And even more weirdly, what if everybody measured the speed of light, the same value for the speed of light, no matter the reference frame? And that is the entirety of what we're going through. Disappeared into the ether, like it. Excellent. Exactly. So Einstein comes along in 1905 and says, okay, let's take that as an assumption that speed of light is constant and there's no ether, and just follow that line of reasoning and see where it takes us. Assume C constant in all reference frames. Actually, this is a little bit simplistic. He actually asserted something called the principle of relativity. Which says that physical laws remain the same in any, let me write this down. Physical laws, meaning the laws of physics, remain the same in any moving, non-accelerating reference frame. Oh, you're not seeing this thing. One such law is that speed of light in a vacuum, I'm not talking about it traveling through mediums. When I say the speed of light, I mean the speed of light in a vacuum, has a specific unchanging value. Everyone measures the same value of the speed of light, no matter their non-inertial, non-accelerating reference frame. Everything that comes next, all that we're going to talk about for the next 2 weeks of class, 2.5 weeks of class, comes from that single statement. Everybody measures the same value for C, no matter what their reference rate. And there's some weird stuff that comes with it. Let's just do a quick thought experiment to show how weird this gets and how quickly this gets weird. Okay, so let's say there's going to be a lot of trains and things in the next couple weeks, so bear with me. You've got a train. Here's our train. Got some wheels on it. And let's say you are on this train and you toss a ball. And you toss that ball up into the air pretty quickly. That ball hits the ceiling, and then that ball returns back to the ground. Okay, so you can measure things like, let's call this D, let's call this, I don't know, L, the height of the train. And so you can say, you can measure as an observer on the train the velocity of this ball, right? This is just going to be 2L divided by delta T, the time that it takes the ball to go up and down, right? The velocity of the ball as it travels on that train. Great, this is all simple. I can show you a better picture of this. Let me show you a better picture of this. Here we go. So, yeah, okay, cool. So let's say now you've got the train and you're not in the train anymore, but you're watching this train go by, right? And so the same experiment's going to happen. This person in the train is going to throw the ball up, it's going to bounce off the ceiling, and it's going to come back down. Let's ignore the fact that it's going to be changing speeds as it goes up. Let's just say that all this stuff is happening fast enough that we can ignore all that. Actually, it doesn't even matter if it's changing speed. This is still going to be the case. Okay, so if the train is moving by and you're on the platform watching it go by, and here's the train, right? The ball might be here when it leaves the ground, but it might be here when it comes back to the same place sometime later after the train has moved after that ball. So as seen from the ground, someone is going to see this same flight of the ball as like this instead, right?
Oh, we can't see what you're drawing.
Oh, that's sad. Is that what everybody's chatting about? Oh, no. Okay, let's see. There we go. It's back now. Okay, basically what I just drawn on the, here is the train at the beginning. When the ball leaves the bottom of the train, by the time it reaches the bottom of the train again, the train has moved over here for this perspective. And so the path of the ball, instead of being straight up and straight down, is a triangular path that looks like that. Make sense? Okay. Does non-accelerating just change speeds, or does it include rotation? Okay, so yeah, non-accelerating means non-accelerating in any way. So we're gonna be talking about what we mean by this more clearly as we go. But I mean no rotations and no speeding up or slowing down, right? So non-accelerating means one person moving through space, relative to the other one in a particular direction. That's special relativity. That's the special case of non-accelerating frames. General relativity, which Einstein came up with 10-ish years later, is the generalizing of that to inertial to non-inertial frames, to frames that are accelerating. But we're not going to cover any of that in this class. We're going to stick to the special case, special relativity, the special case of non-accelerating frames. Okay, so you could calculate, the person on the ground would say, what is the velocity of this ball? Well, V is a heck of a lot more than 2L, right? Whatever this is, delta D divided by delta T, right? And so the delta T that these two people measure are the same. This delta D is going to be way bigger than 2L, depending on how fast this train is moving. And so we expect, let's say this is V1 and V2, that V2, the velocity, this person's going to see the ball moving much faster than the person who's on the train. They'll observe different velocities for those two things. That make sense? Okay, now let's replace the ball with a laser and do exactly the same experiment. Now, instead of throwing a ball, we're going to shine a laser from the bottom of this, bounce it off a mirror, and then have that laser come back down. And now, instead of this person on the ground seeing the ball do this, the person on the ground sees the laser have a path that looks like this. Everything else is exactly the same. Obviously, this train has to be moving pretty darn fast for the path to look like this. Maybe it won't be that stretched out, but you get the idea, right? Any motion that this train has has to elongate the path that this laser seems to take for somebody observing it from the side, right? The difference here is that for light, those two observers are not allowed to see a different velocity for that light. They are not allowed. These two V's must be the same for light. They must all be equal to c. Everybody has to measure the c for the speed of light, no matter what their reference frame. So what does that imply? Well, we know that this path has to be longer than this path, and yet we know that these two velocities must be the same. What does that imply? There's only one other thing in that equation that you can change.
The delta T changes.
The delta T has to be different for those two observers. they must be somehow experiencing time differently. So that's where this whole thing starts and gets weird. With that one assumption that they have to measure the same speed for light, you can show that these two observers must be experiencing time differently, or at least experiencing a different delta t for exactly the same phenomenon, meaning the time it takes a laser to bounce off a mirror and come back. And that's pretty cool. And so this thing that we thought of as immutable time is in fact not quite as immutable as we thought it was. Okay. So that's the cool thing. That's where we're going. We need to wrap our brain around that first, obviously, but we also need to build up some notation and some nomenclature. So let's take a step back. We'll come back to the lasers and the train. Let's take a step back and do some more mundane things too, and talk about the physics of different moving frames and how we measure velocities and different distances and things like that. This is a little bit, yeah, I posted an announcement today about a video I wanted to watch, excuse me, that is very much related to this topic, which I think does a fantastic job of laying out the concept of space-time diagrams and really what we're plotting. So I encourage you, if you've not already done so, to go over that. Let's just talk about some things we need to go and know before we go too much. Okay, so let's think about axes, right? And think about two different kinds of axes that we could draw. So we're used to drawing XY axes. Here's our x-axis, here's our y-axis. Let's just try offsetting two axes. The simplest thing we could do. Okay, so we could imagine some other coordinate system. Actually, draw these in different colors so it's a little bit easier to see. Since I've got two colors, let's use them. So we might have somebody else. Again, usually you set your coordinates to a place where you are at the origin, right? So you can imagine somebody sitting here at 0, 0. You can imagine somebody else sitting at somewhere else and call this x prime and y prime and say, well, we're not moving with respect to each other, but we're not at the same position either. So I'm going to call, the red person is going to call this one 0, 0, the origin, and the black person is going to call this point 0, 0. And so they do not agree on what those x and y values are. So this is pretty easy. You can do transformations, right? You can transform from one position to another. It's not that hard. X is equal to x prime plus x naught, and y is equal to y prime plus y naught, right? X naught and y naught just being the difference in the origin points. Okay, this is simple, but it's not very interesting. More interesting is going to be a moving reference frame. So let's say we have the same thing where we have two different people, but now one of them is actually moving with respect to the other one, right? How about a moving reference frame? Let's say, and we can define our coordinate axis anywhere we want to. So let's say that the prime observer is moving in the plus x direction with respect to the non-prime observer. And it doesn't matter if which direction they're moving really, up, down, sideways, backwards, left to right. We can define the x-axis to be that direction. If one observer is stationary, the direction that the other one happens to be moving with respect to the first. So let's say in the plus x direction. Again, we're free to rotate our coordinates so that this is always the case. So we've got two equations here. X equals x prime plus x naught plus vt. We've got an extra term here where v is going to be how fast the frames are moving with respect to one another. And y is equal to y prime plus y naught. The y actually doesn't change at all, right? It's only the x one that changes over time. So how do observers see velocities? So we know, and I'm not going to call these V's. I'm going to say ux is a velocity of an object in the x direction as seen from the non-primed observer. I'm going to reserve v for denoting the velocity between the two frames, and u is going to be a velocity within that frame. Okay, so we know that u is just dx dt, and that is d dt. If we want to convert that to the prime frame, we can plug this in. X prime plus x naught plus vt. This is going to be dx prime dt. X naught's a constant, that actually goes away, plus v. And this gives us u prime x plus v. And this makes sense, right? If one reference frame is moving with respect to the other one, they're going to measure different velocities for something moving through that space, right? They're going to measure, and they're going to be different in the x direction by this velocity difference between the two frames, right? Uy is going to be similar, except there is no v term, right? This is just dy dt of ddt of y prime plus y naught. This is just dy prime dt, which is just vy, u prime y. So it makes sense, right? The velocities in the y directions are unchanged. Everybody says the same for the perpendicular to the direction of motion, and they're different in the direction of motion just by this velocity between the frames. Okay, what about accelerations? I don't have nearly enough whiteboard space here, so I'm going to do it over here. For accelerations, I know that ax is d ux dt. That is d dt of this thing down here, u prime x plus v. At the subscript x. Right, u prime, v is constant now, and so this goes to 0. This just becomes the u prime x dt, which is just a prime x. So everybody measures the acceleration the same for everybody, right? An observer in the unprimed frame will see exactly the same acceleration as the observer in the primed frame. And I'm not going to do it. Ay is all equal to a prime y. So everybody sees the same acceleration. Everyone agrees on acceleration. Everyone also agrees on lengths. I'm not going to bother to derive it, but you can see, hopefully, that delta x is the same as delta x prime. Everybody agrees on distances between objects or lengths of things. Everybody agrees on acceleration. People do not agree on relative velocities of things, or obviously relative positions of things. So let's define some nomenclature here that they mention a little bit in that video that I asked you to watch, but they don't define them as terms. If everyone agrees on something, we say that's an important thing. Regardless of reference frame. We call that covariant. So things that are covariant are length, or delta x, any distance and difference in position, time, acceleration, force, things like that. Things that are not covariant, things that will vary depending on what frame you're in, things like velocity, things like kinetic energy, things like potential energy. These things will be conserved in all reference frames, but every reference frame will have a different value for them specifically. Obviously, if velocity is not conserved, then neither is kinetic energy. Okay, So that's some nomenclature and some just ideas to get out of the way. We need to think now about specific plots and specifically space-time diagrams. And I thought the minute physics thing did a fantastic job of laying this out. I'm going to talk a little bit about this in a slightly different context. If you have not watched that video, I encourage you to do so ASAP. So we can plot the motions of objects, and it is convention, and it kind of makes sense, and you'll see why as we go along, that we make plots in space-time diagrams in special relativity in a particular way. So you're used to seeing time almost always as the x-axis, right? Things, you're seeing the positions of things over time, or the prices of things over time, or anything. We usually have time as our x-axis because it's sort of the thing that is always moving along in a particular direction. Space-time diagrams, let's flip them. So in space-time diagrams, the t-axis is almost always the y-axis, and the x-axis is almost always the x-axis, which makes sense, right? We have an x-axis where an x-axis should be in the x direction. That's one reason why it kind of makes sense. So this is a diagram, and again, it takes a while to wrap your brain around this for plotting one-dimensional motion as a function of time, right? We are interested only in the position of an object along the x-axis. We would have to have a much more complicated diagram if we wanted some two-dimensional view, but we're almost always going to be thinking about this in a one-dimensional sense. And since these are non-inertial reference frames and nobody's accelerating, we usually take this to be the different direction of motion, the x direction. We can define it whatever we want. Okay, so we can, again, each one of these horizontal strips is a snapshot of where our object is at a given time, or where our set of objects are at a particular point. So I'm going to do a slight thought experiment. Again, we've got the reference frame of the whiteboard that I've got down here, and I've got the reference frame of this ruler. This ruler, I'm going to slowly move across the page at some constant fixed velocity, right? And I'm going to think about the location of a marker, and it's going to be moving relative to both of them, right? So I'm thinking sort of two reference frames here, and I want to plot this as from the reference frame of the board first, right? So maybe I can just, no, let me do it first. Okay, so I'm going to call this 0 maybe. This is my origin. And as I go along, I'm going to move the ruler to the right, and I'm going to move the marker, and the marker is going to move into the right faster. And then all of a sudden, the marker is going to turn around and come backwards for a minute, and then it's going to continue back again, right? Let me do that again. So they start off together, the marker and the ruler lined up. The marker moves faster than the ruler to start. Eventually, it stops, turns around, and comes back. And then once it reaches the origin, it keeps continuing moving faster and faster and faster again. So let's think about plotting the position of this marker as a function of time from the perspective of the board, right? From the rest perspective of the bottom, right? So what's it going to look like? It's going to start off at the origin, right? It's going to start off at 0, 0, x equals 0, and t equals 0. That was this point, right? And we know it's going to start moving. If we define this to be the plus x direction, what's it going to look like?
Oh, it'll basically be moving forward, but it'll have like a curve back every now and then.
Yeah. So certainly it was moving forward, sort of. Let's say in a I don't know if I successfully did that in a constant velocity rate, but let's say it was some constant velocity rate like this. And then it came a point at which it turned around, right? What's it going to do then?
Zigzag back.
Yeah, again, time is always progressing forward. So, but this thing turned around and actually went backwards for a moment until it got to the way the ruler was. Now it didn't, is it going to get all the way back to 0? Let's do it again. Wasn't very good. again, this is the perspective of the board itself. Did it get back to again, the two agreed. The marker, let's say the marker and the ruler frame and the board frame agreed that 0 was 0 at this point. They no longer agree that 0 is 0 anymore. And then the marker went back to 0 on the ruler, it kept going, but it never did get back to this 0, right? And so it might look something like this. And then it continued on again, right? That might be the world line, meaning the collection of points that this marker occupied as a function of time as it traveled that path. Does that make sense? Yes. Okay. What if we chose a different coordinate system? In other words, what if we chose the coordinate system of the ruler? What would this same curve look like? This is the board frame. Sorry. Say it again.
Would it look like a triangular sine wave going upwards?
Yeah, kind of. How is it related to this? How would I have to shift this one to move it onto the, let's call this x prime t prime frame?
Would it be the same or similar graph, just sort of compressed towards the t-axis?
Yeah, compressed towards the t-axis. That's interesting. Well, we've got a reference point here, right? We know what the x prime value of the marker was at that point, right? What was it?
That should be at the x prime equals 0.
Right. Remember when I went through, it got to some high value and then it got back to the ruler 0 before it started going off again, right? So this we know has to be x prime equals 0, right? And so it's going to look similar to that, but it's not going to be moving as fast. And then it's going to move back to the origin, and then it's going to be not moving as fast again, right? So yeah, it's going to be somehow compressed back to the original t-axis. It's interesting. We can actually plot both of these axes on the same plot if we want to, and this is where things get really weird, right? If we were to plot the t prime axis on this plot, where would it go?
Would it just follow the line you've drawn?
No, the t prime axis. I assume you're talking about this line.
Yeah, I don't know.
That is the world line of the marker. But remember, the t prime axis follows the ruler, and the ruler is following a non-inertial frame, meaning it's not accelerating. It can't change directions. It can only move slowly forward in one direction, right? And so, well, it's pretty easy. It's the world line of the origin of this ruler. So what is that going to look like?
Would the t prime axis be on that one point where the marker shifted?
Yeah, we know where two of these. We know that the t prime and t axes have agreed on that 0 is 0 at t equals 0, and we know that this is also on that axis. And so all we have to do is connect those two lines and continue them. That must be the t prime axis, which is weird to think about, right? So we can think about, I'm almost out of time. What do I have? Another minute? Yeah, another minute. We need to think about a transformation, right? That takes us from the t axis to the t prime axis and back again, right? Basically, we've already written it down. This is the moving coordinate frame in the x direction. So if you're thinking about transforming this to this, what do we have to do? Is this a a translation? Is this a rotation? Is this a scaling? How would you describe if we wanted to, let's say, take this and transform it onto one where the T prime axis is the preferred perpendicular axis?
Looks like a rotation.
It does look like a rotation, doesn't it? A rotation, though, is going to be problematic, and I'll tell you why. Because a rotation is going to imply something interesting about these two events. If I just take this and rotate it back, I am implying that these two events occur at different times.
Also, wouldn't a rotation also have to rotate the x-axis, because it's just right now T prime is not 90 degrees to the x.
Right. And also you have to think about rotating the x-axis. That's exactly right. So, and do we want to rotate the x-axis?
No, I don't think we do.
Right. We'll think about what rotating the x-axis means, but that's going to be weird, right? Rotating the x-axis is going to lead to some very weird things. So for now, let's assume that we don't want to rotate the x-axis. So a simple rotation is probably, as Isaac suggests, not what we want to do. I'm out of time for today, but this is a good exercise to think about for next time, and it may be even mentioned in the video. I didn't want to watch it to the end. How exactly we're going to take this point and move it over here, and then also what's going to happen to this axis when we do that. So we'll ponder those things and come back and talk about those things on Wednesday. So I will stop there. Hope you're having a lovely Monday. Loving your cat, Brian. Well done. And we'll pick this back up on Wednesday. Bye, everyone.
Thank you.
Awesome. Yeah, thank you.